Okay, so this is Chapter 3, Lesson 1, and I'm actually going to start in the middle of the chapter, and I'll explain why in a minute. I'm going to actually start with Section 3.8 to 3.9, and this is on pages 103 to 108. And it's all about making sure that everybody has the same baseline. I don't want to start right in with the math before reviewing chemical equations, types of chemical equations, and balancing equations. So conservation of mass and chemical changes. The law of conservation of mass was first discovered by Antoine Lavoisier, and we all know what that says. It states that matter is neither created nor destroyed, but rearranged. So what we know then is that what we start with as the reactants, that must equal our products. And just to explain this in layman's terms, in Regents Chem, if you had reactant A plus B and it yield C, and they said that you had 23 grams of A and you had 100 grams of C, they wanted to know how much you had of B. And this is simply a most basic algebraic equation, 23 plus X equals 100, and we solve X to be 77 grams. So now we're talking about stoichiometry. And what is stoichiometry? I'm just going to abbreviate it. It's the study of the quantities of the substance consumed and produced in a chemical reaction. And for those of you that didn't have me last year, I abbreviate reaction RXN. So now we're going to study the amount of AB used and the amount of C produced. That's basically what stoichiometry is in a nutshell. And what are chemical equations? Well, simply, they're used to represent chemical reactions. All right, I'm going to go through some basic review of parts of an equation and balancing an equation and different types of equations so that we're all on the same playing field. So remember, coefficients, when we balance an equation, we change coefficients only. Remember, the triangle means change. This changes, when we change the coefficients, this changes the amount or quantity not the identity. So when we balance equations, we change coefficients only, and that's why. We never change subscripts. Never, ever, 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 when we're balancing an equation. Never change subscripts. Because that changes the identity. So instead of H2O, we might have H2O2, which is clearly not the same thing. So let's go ahead and look at some balancing. Remember that your arrow is always your equal sign. So I'm going to rewrite this over here. Just give me a second. I'm not going to write the states right now so that it's easier for me to get through this. So remember, this is my equal sign. Number of atoms on the left have to equal the number of atoms on the right. The big question is, where do I start? Well, I tend to start with polyatomic ions. So we have a polyatomic ion here, PO3. But PO3 is not intact on both sides of the reaction, so in this case, we don't need to start with PO3. What I don't want to start with is H, and I'll tell you why. Because H appears in one place on the left side of the reaction, but in two places on the right side of the reaction, which is going to make balancing more complicated. So I'm going to pick Cl, only because it stands out obviously to me that there's 3 here and 1 here. So I'm going to put 3 here. And I have 1p and 1p, I'm good. But now on the right side of the equation I have 3 H's here and another 3 here for a total of 6. So if I put a 3 here, that will give me 6 H's, and I have 3 O's, which I have. So my equation is balanced. And you can either put a 1 here in front of these, or you can leave it blank. All right, second equation. Mg3n plus H2SO4 yields MgSO4, and that's not going to fit. NH4 2SO4. So we've got magnesium nitride, sulfuric acid, magnesium sulfate, and ammonium sulfate. Well, here's where I say let's look at the polyatomics first, because our polyatomics are intact. I have an SO4 here, and I have SO4 here and SO4 here. The only thing that didn't stay intact was my NH4. There's no NH4 on the left. So the first thing that I notice is I've got 2 SO4s on the right and only 1 on the left. So I might be tempted to put a 2 here. However, I notice that Mg is attached to this SO4, so that I have to worry about my Mg's, because I have 3 here and only 1 here, which is going to affect my SO4. So I'm going to start with the Mg's on this one. I have 3. So I'm going to put 3 here. So now I have 3 Mg and 3 Mg, but I have 3 SO4s here, and 1 here is a total of 4 SO4s. So I need to put a 4 here. Now I have 4 SO4s. Now I have a total of 8 H's, which I do have here. 2 times 4 is 8 H's. And I have 2 N's. Oh, I made a typo on that. That should be N2 there. I was like wondering why that wasn't working. This should be Mg3N2. You probably like, Miss Nielsen, you didn't copy that right. All right. And there we have it. Now we're balanced. Let's look at the next one. NH4, NO3 yields N2 plus O2 plus H2O. So, let's see. Nothing stayed intact. I definitely don't want to start with O, because O is in 2 places on the right. I can either start with H or I can start with N. Doesn't really matter. So I have 2 N's on the left, right, and 1 on the left. So I'm going to start with my N's. I'm going to make this a 2. So now I have 2 N's, 2 N's. Now I have a total of 2 times 4 is 8 H's. So I'm going to make this 8 H's. And now I have 4 O's here, 2 O's here, which is a total of 6 O's, and 2 times 3 is 6 O's. So I'm balanced. I don't think I have to review this, but G, L, S, and AQ. These are the states of matter that you see written after each of the compounds. G for gas, L for liquid, S for solid, and AQ for aqueous, meaning with water. Later on, as we start to look at reactions, when you see an arrow with a triangle over it, it could be under it too. This means heat. So it means that heat was added to this reaction, probably as a catalyst. Using patterns of reactivity to predict behavior. So meaning, recall burning magnesium ribbon and copper wire. We know that certain materials will act a certain way because of their placement on the periodic table. So the first thing is group 1 metals, which are our alkali. They have a +1 oxidation state, and they are highly reactive. And the biggest thing about them is that they don't occur freely. And for those of you that have had me, you've heard me say you can't go in your backyard and dig up a chunk of sodium. It's always going to be attached to something. Sodium chloride, sodium bromide. It's going to be usually in a compound with a halogen. Group 2 are our alkaline earth. These have a +2 charge, and they are also very reactive. Not as reactive as our group 1, but still very reactive. All of these, group 1 and group 2, are malleable, meaning bendable. Ductile, meaning they can be drawn into a thin wire, and good conductors of heat and electricity. Remember, because they are in the same group, that, well, all group 1 metals behave very similarly when they react with other elements, and all group 2 elements will react very similarly when with other elements. Let's talk about some common reactions. Now, your book doesn't go into this in this unit, but I really think it's important as we start to do the math that we have a solid foundation. So A, B, C, D. I'm going to review 4 basic types of reactions. Combination, which you know as synthesis. Combination is just another word. Decomposition. This is going to be a new word for you. Metathesis. And these are just your double replacement. And combustion. All right, so let's start with combination reactions. So, combination. Two or more reactants, one product. Usually have the general basic format of A plus B yields AB. And let me give you 2 examples. So the formation of magnesium oxide from magnesium solid and oxygen gas. That's one example. Or the formation of calcium hydroxide from calcium oxide and water. So you will learn this year in one of the units that any metal oxides, when added to water, will make a base. So that's combination. Decomposition. Often referred to as the opposite of synthesis. I usually refer to synthesis as marriage and decomposition as divorce. Single reactant breaks up into 2 or more products. Usually has the basic format of AB yields A plus B. Copper carbonate example, CuCO3 yields copper oxide and CO2 gas. You will learn that whenever carbonate is involved in a decomposition reaction, it will result in carbon dioxide gas as one of the products. Just another example here, we can do the opposite of the synthesis. We can take copper hydroxide and it can form copper oxide solid and water. Metathesis. as I said to you early, are double replacement reactions, and they are a reaction in which the anion and cations, anions and cations, switch partners. I used to refer to this as swingers. They have the general formula AX BY, AX plus BY, sorry. AX plus BY yields AY and BX. Two examples. First one, let's do silver nitrate. And salt, water, and that's going to produce AgCl and NaNO3. And this is a precipitate, and this is going to be aqueous. Now, how did I know this is a precipitate? Because I don't have table F available. I am going to, not in today's lesson, but in a future lesson, teach you solubility rules by an acronym called NACL-NO-SO, which will help you remember what your insoluble compounds are. Another example is FeO, iron 2 oxide, plus HClO4, and that's going to yield H2O and FeClO4 too. Aqueous. So let me just, I'm going to write these three down, and then I'm going to talk a little bit about them. And the last example, you're probably wondering why I'm giving you three, but it'll be evident. You don't have a spot for a third one, but you have a notes section. Na2, NO3, solid, plus HCl. NaCl, aqueous, plus, oops, I'm going to run out of room. Let me erase this. I need to fit this on here. I'm going to go over here to the left with it, but it's still part of this equation. Plus H2CO3, aqueous. And then what happens is the H2CO3 further breaks down into H2O and CO2 gas. Gas, liquid, aqueous. All right, so let me talk a little bit about what's happening here in metathesis reactions, other than the obvious. So remember, they take the format AX, BY, and then they switch partners AY, BX. So here, Fe's plus 2, oxygen's minus 2. And you've got H is plus 1, and the ClO4 ion is minus 1. So positive hooks up with negative. So Fe hooks up with ClO4. Okay, so that's what we have here. But because the Fe was +2 and the ClO4 was -1, when we dropped and crossed, this 2 came down here. That one's done. And then my H here hooked up with my O and made H2O, because there was 2 H's here and 1 O. That one's pretty evident. Okay? And I formed liquid water. All right, that's that. Whoa. Alrighty then, that works. We formed liquid water. Then, up here, I had Ag, which is +1, NO3 is -1, Na was +1, Cl was -1. My positive hooked up with my negative, so my Ag hooked up with my Cl, my Na hooked up with my NO3, and I formed a solid. In my last one, Na was +1, NO3 was -1, H was +1, Cl was -1. Well, this was easy. 1, 1, 1, 1. Na hooked with Cl, 1 to 1, and H I wrote this wrong. Crap. I'm sorry. This should have been CO3. Okay. Okay. Sorry about that. So my Na hooked up with my Cl and my 2 H's hooked up with my CO3 to make H2CO3 aqueous. However, in this reaction there was a second reaction that took place, and that was the decomposition of the carbonic acid into water and carbon dioxide gas. So a gas was produced. Which brings me to 3 important conclusions about this. In a metathesis reaction, or double replacement, we look for 3 things. We look for the formation of a precipitate. PPT is precipitate. Formation of water, or the formation of a gas. And that gas, you know, can be CO2 to stable gas, or H2S. There could be other stable gases, but those are just 2 off the top of my head. That's terrible. My handwriting here. So, in a double replacement reaction, what I'm trying to tell you is if we don't have the formation of one of these 3 things, then a reaction doesn't take place. So when I put salt in water, NaCl and H2O, there's no reaction because I don't form a precipitate, I don't form liquid water, and I don't form a gas. The 2 just dissolve in one another. There's no reaction that actually takes place. All right, that reviews reactions, and you're not going to see any of that in the book. But I do have one more reaction. Sorry. Combustion reactions. Okay. Combustion reactions. These are rapid reactions that produce a flame. They have a basic format, and that format is CHY. Some type of hydrocarbon plus oxygen yielding CO2 and water. So let's look at two examples. The first one I'm going to give you is an easier one. C3H8 plus O2 yields CO2 plus H2O. And we have to balance the reaction. So right away I see I have 3 C's, so I'm going to put a 3 here. I have 8 H's, I'm going to put a 4 here. So that gives me 3 times 2 is 6 oxygens plus 4 oxygens over here is a total of 10 oxygens, so I need a 5 there to balance the equation. That's straightforward. Now I'm going to give you one that's not so straightforward and a little trick that makes things easy. C2H6 plus O2 yields CO2 and water. Alright, so I see right away I have 2 C's, so I get going, I put 2 here. I have 6 H's, I'm going to put a 3 here. But then what happens when I go to balance my O's, I see I have 2 times 2 is 4, plus 3 O's is 7 O's. Well, that's not going to work because I have O2, so I can't have 3.5 O2. So as soon as you get yourself into a situation like that, what you want to do is go back and double everything. So I'm going to double this, I am going to double this, and I'm going to double this. Now I've got 4 times 2 is 8 oxygens plus 6 oxygens is 14 oxygens, so I know that that has to be a 7, and I'm done. So if you get into an uneven number, go back and double all of the coefficients that you have thus far, and then just finish it up. Okay. So when I talk about reactions and I say, as I gave the example today, why you need to know your polyatomic ions, because when I say solid mercury 2 sulfide decomposes into its component elements when heated, you need to be able to write a reaction. So mercury is Hg, I know it's Roman numeral 2, sulfide is sulfur, so that's -2, so it's simply HgS, and it is a solid, so I put the solid, decomposes, so that means my arrow, into its components when heated, so I know that there's heat here. So its components are Hg and S, and mercury we know is a liquid at room temp, and sulfur would be a solid. Another example, the surface of aluminum metal, so I know I have aluminum solid, undergoes a combination reaction, so I'm forming something, with a reaction of air. Remember, anytime we write one of the Brinkelhoff elements by itself, it has to be O2. And we know that oxygen is a gas. So they form a reaction. So we have Al and O. We know Al is +3, O is -2, drop and cross, I get Al2O3. However, this is not balanced. If I have 2 oxygens here and 3 here, my least common multiple is 6. So I'm going to put a 3 here, a 2 here. My oxygens are balanced, but now I have 4 Als. Si2H6 burns when exposed to air. So here they gave me my reactant, Si2H6 plus O2. yields. Now this isn't straight combustion. This is a special one. Your silicon is going to combine with your oxygen, and I wouldn't expect you to know this, SiO2 and H2O. But we still have to balance it. So I have 2 Si's, I have 6 H's, so that's a problem. So right away I get into an even amount. I have 4 and 3 is 7, so I'm going to put a 2 here. I'm going to switch this to 4, and I'm going to switch this to 6. So 4 times 2 is 8, and 6 is 14, so this is 7 again. Write a balanced equation for the combustion of C3H6O in air, which is acetone, C3H6O plus oxygen. And this one's going to be, since it's all organic, is going to just be CO2 and water. But we have to balance it. So I've got 3 C's, 3 C's, 6 H's, now I have 6 H's. 3 times 2 is 6, plus 3 O's is 9. So that's not going to work, right? Oh, yes it will, because there's one over here. So I can change this. I almost missed that. Move this plus sign over. So I can make this 4. 4 times 2 is 8, plus this one is 9. So 9 O's. And then over here I have 6, 7, 8, 9 O's. I'm good. All right, last one. Write the balanced equation for a metathesis reaction between hydrogen sulfide gas. H is +1, S is -2, so dropping across. Gas reacts with iron 3 hydroxide, FeOH. This is -1. They said it was iron 3, so FeOH3. And this is aqueous. So they switch partners. So remember, H is +1, S is -2. So Fe is going to hook up with the S. And this was +3, so that's going to come here. S was -2, that's going to go there. And we have H and OH, so we have water. So now we just have to balance this. Right away I see 3 sulfurs, I'm going to put a 3 here. I see 2 irons, I'm going to put a 2 here. That gives me 6 H's here, 2 times 3, 6 H's there, 12 H's. So we need a 6 here. And that gives me 6 O's, and then I have 2 times 3 is 6 O's. So we're balanced. So as I said, Chapter 3 doesn't go into any of that, but I wanted to make sure we had a strong foundation. They talk about equations, balancing equations, but I wanted to lay the groundwork for some of the more common types of equations that we will be dealing with in this chapter. And the next lesson is going to be about math. Fasten your seatbelts.